Hey everyone, we're Group 8. Our project is simulation of swarm of unmanned ground vehicles. We're also doing physical implementation. But anyways, I'm Carter Nichols. I'm electrical engineering.
I'm Charles LaFleur. I'm electrical engineering.
I'm Jefferson Charles. I'm a computer engineer.
I'm Chase Gallo, electrical engineering.
I'm Justin McDonald, computer science.
Summary of our project so far is the main objective has been to install ROS2 Swarm on each robot. They need to be installed on each Raspberry Pi. Doing this will help us test different basic and advanced movement patterns. And it'll help us understand the swarm communication functions and the capabilities of those functions. It'll also help us determine if ROS2 Swarm is fully decentralized or not. Our approach to this was utilize these packages and also utilize a network sniffer on the network. And we determined that no packages were sent directly between each Turtlebot while running different basic and advanced movement patterns. We also used a built-in RQT graph package for ROS2 Swarm that will illustrate all the nodes being published and subscribed. And it'll further prove that the robots only publish and subscribe to nodes that are shared and not directly to each other. This proves that it is a decentralization of the system.
So since our last update, we were really struggling with implementing ROS2 Swarm onto the Turtlebots themselves and onto the Raspberry Pis themselves. And this was mainly due because our environment variables were not properly being sourced by the shell terminal and by the bash. And it was due to that, and also the namespacing of each robot was not properly defined because each robot needs its own namespace, so that way there's no conflicts between nodes and topics. Um, Now that we have ROS2 Swarm actually installed and working on each Turtlebot, we're beginning to execute the patterns, and as Charles just said, we're observing the communication between them, making sure it's a fully decentralized system and fully distributed. And on this picture, in the screenshot in the bottom right, we can see two terminals that are diagonal of each other are the Turtlebots running the ROS2 Swarm package. The bottom right terminal is us executing the commands, and then the top left terminal is us using the network sniffer to look at the data being sent between them. The data being sent there is just us pinging the robot to make sure we're actually reading packets. But as Chuck said, the robots don't actually communicate to each other, as you can see.
Okay. So once we were able to get Rust to Swarm working and successfully working on the Autobots, we started implementing different movement patterns. And the two main ones that we were able to do were attraction and dispersion. Attraction where the Autobots come closer to each other, and then dispersion when the Autobots disperse from each other. And since Rossi Swarmer's fully decentralized system, within the patterns, there's no robot to robot communication. Um, the Autobots uses the lidars to uh, see for nearby objects if that object is a Autobot, depending on the size of that object. And if the Autobot using the lidar sees that object being the same size as this Autobot, it attracts and disperses from it. And below you can see the RQT graph that we have. And like Carter mentioned before, once we execute, or once the host computer executes the swarm command, that's published in the global namespace. And each robot has its own namespace. And within that namespace, the robot publishes and its own nodes and topics and um, subscribes to different topics that it needs to execute that swarm command.
So we also customize some of the user end behaviors when running Rasta Swarm. and different movement patterns and connecting to the Pi on the Turtlebot as well. So it's easily automated where you just enter the last digits of the IP address for the Pi and it'll automatically connect. And then there's a shell script we also created, which gives shown on the right in the top right image, which shows all the different movement and voting patterns that can be selected to run on that robot. And afterward, you would have to go on the laptop and start the command from there, and everything will run. We also had some trouble with running some of the movement patterns like drive pattern, attraction, and dispersion. And so in order to achieve the desired behavior for those patterns, we had to edit the YAML files, which describe all the parameters that control the functionality for the pattern. So for example, on the right, we have the dispersion YAML file, which we can set the max range, which is currently at 3.5 meters. So that this means that the robots, once they've dispersed and are minimum max 3.5 meters apart, they will stop moving based on the dispersion linear if alone parameter is 0. So once they've reached 3.5 meters apart, they stop moving because the velocity is 0. And there were other YAML files like the hardware protection layer, which we had to edit so that robots wouldn't crash into objects or each other. And for that, we had set it to 0.12 meters so that they maintain a minimum distance based on the size of the Turtlebot and have some extra buffer so that we ensure there are no collisions.
So now that we have some of the basic movement patterns working and the Turtlebots are properly executing the patterns and there's not many collisions going on, now we're going to try to move to our next step, which is implementing more advanced patterns. To do this, we need to get some of the voting patterns working. And currently, we're having issues with executing the voting patterns. It seems that one of the defined functions in the voting pattern Python script called getRobotID is not being able to properly find the robot's namespace. So it's not being able to assign a robot ID to each robot. And so this is causing the process to die. For example, we would execute a majority rule pattern and the process would die and nothing would really happen. And that's a big issue that we're facing right now. But we believe once we get the voting pattern working, it facilitates robot-to-robot communication by creating a topic in the global namespace. Now, since the topic's in the global namespace, the system is still fully decentralized because there will be no single point of failure, and we'll test this once we get the pattern working. And once we get the voting pattern fixed, we're going to be able to execute more advanced patterns such as disgust dispersion, where each robot votes on a distance to disperse. Instead of us defining it, the robots are each going to randomly vote, and the majority rule will define the distance that each robot disperses.
We also want to create our own pattern to challenge ourselves and demonstrate Rastoswarm's ability to create new patterns. The current idea for the new pattern we have is called cat and mouse, where one robot would be designated as the cat that would chase the other robot, which would be designated as the mouse. We're thinking about using the mouse by controlling it manually right now. However, this is going to be very difficult as there's a lot of predefined functions for vector and matrix calculations. So first, what we're going to do is we're going to take an existing pattern's files and copy those files under a new name and put them into the setup file And what we're going to do is we're going to test to see if that new pattern, in a sense, runs on simulations and robots. This is so to test that the files are actually being read, that they actually work, so that we know that we can actually start customizing the pattern and start creating this new pattern so that we can start making some real progress.